Hello, and welcome to our presentation on retrofitting a city school. We are Regeneration from Ryerson University in Toronto, Canada, entered in the elementary school division of the 2021 Solar Decathlon Design Competition. Our Lady of Perpetual Help is a Catholic elementary school in Midtown Toronto. The Toronto Catholic District School Board and the school are looking to renovate the 100-year-old building to both solve some issues and bring it up to current performance standards. Regeneration understands this project is bigger than just one school, as there are many similar heritage schools in communities throughout the city. The restoration of Our Lady of Perpetual Help sets an example for renewing treasured schools and communities in urban centers. To introduce the team, I'm Steph, joined by Noel, Ghazal, Keziah, and Shirin.
As a retrofit, the project is constrained to original form and function, as well as existing issues. The school is located at 1.5 Garfield Avenue in Midtown Toronto, and this area is an urban environment with a mix of natural trails and parks that provide a connection to nature within city life. In the last 5 years before the most recent census, the city ward that the school serves has seen a population growth of 6%. So to accommodate an estimated 12% growth in the next decade, the school is designed for 400 students and 40 staff. And these intended occupants, as well as its community, are our target market, along with the local school board, which is the TCDSB, and stakeholders in the construction industry. As the school board has recently adopted the motion to become net zero energy, we aim to align our project goals with the board's energy conservation plans, as well as some plans to accommodate growing enrollment in the future. Throughout our project, we also kept in mind a construction time limited to make sure the school remains open throughout the year, as well as keeping project costs low. In design, we worked to provide solutions for a cold climate of Toronto that not only complied with building codes, but also achieved targets for energy efficiency in the Toronto Green Standards. These are the city's own sustainable design requirements that set increasingly rigorous performance tiers, and we aim to achieve Tier 3.
In this project, our goals include minimizing embodied and operational carbon, minimizing energy consumption, maximizing usable space after retrofit, responsible water management, optimal occupant comfort and well-being, enhanced occupant experience, and finally community integration. To achieve our design goals, decisions are made by all disciplines, and design solutions involve considering the impact of all disciplines on each other. In addition, passive and active design strategies were incorporated in this project. As we align the details of our design through contest challenges, I will start with architecture. Our Lady of Perpetual Help Elementary School is a masonry building built 100 years ago, similar to most architecturally significant buildings in Toronto of that time. The first building was built in 1922 and was extended by 2 additions in 1963 and 1966. Currently, the school has two stories and a basement that includes 11 classrooms, 4 kindergartens, and a gymnasium. Moving on to the redesign of the school, we added an atrium to the center of both wings, replaced the 1966 building with a new extension, and created an outdoor study space. In addition, we added shadings to the parking to create more room for solar panels, defined a walking route around the school site for students, and added permeable pavements for rainwater collection and bioswales to reduce stormwater runoff. And finally, wastewater will be recycled in an on-site delivery machine. The atrium is vented naturally as well as providing daylight into the school, and installing horizontal shadings over windows reduces cooling loads in summer. The atrium defines entrance to the school and brings transparency to the design. To preserve the historical character of the school, the timber structural elements of the atrium were inspired by pointed arches of Gothic architecture. The new extension includes a gym, a multipurpose area, a library on second floor, and an outdoor study space. The multipurpose area follows a biophilic design and has capacity of all the occupants of the school. And the outdoor study space with exposed timber creates a warm ambient for students to study and spend time in. Finally, by internal insulation of the envelope, the school will be upgraded while preserving its heritage.
The original structure of the school is triple wide mass masonry with wood frame roofs and wood frame reinforced concrete floors. Majority of the school doesn't show major signs of failure, but there is one failing control joint near the old gym that will be removed. In the redesign, mass timber is selected. Glulam columns, beams, and trusses are used with down laminated timber or DLT panels. DLT is a standard lumber product that doesn't use glues or nails, but instead dowels to friction fit boards together, which further reduces its environmental impact. The retrofit envelope addresses existing concerns as well as preserves the brick facade by insulating masonry from the interior. In a cold climate, however, insulating masonry from the inside leads to colder, wetter bricks with more risk of freeze-thaw deterioration. So, our values near the low end of passive house levels are chosen to balance thermal performance without over-insulating. To accommodate drying, the retrofit walls are vapor open with stone wool rigid and stone wool bat insulation and wood stud walls that are used for interior finish support. Most elements in the wall are inorganic except for the studs, but WUFI analysis showed us that drying is adequate since relative humidity stays below 80% throughout the year. In basement slabs, GPS insulation with a dimpled drainage mat is used, and radiant heating panels are on all floor decks as part of the building's heating strategy. To minimize thermal bridging, spray foam is used at transitions to achieve low psi factors that meet passive house standards. For the timber extension, our values achieved are slightly higher than the masonry envelope. Walls and roofs are insulated from the exterior for continuity of the thermal control layer. Stone wool, rigid insulation, solar cladding, fiberglass clips, and a smart vapor retarder is used in walls. GPS is used in the ground slab, and on each floor, heating panels are again installed. For windows in the school, new triple glazed low E units are installed. Units with a high heat gain coefficient are in most parts of the building for passive solar heating, while units with a lower coefficient are installed in the south facade and atrium. Water management aims to reduce consumption by replacing old fixtures in the school, and by doing so, an estimated 52% reduction compared to baseline is achieved, which meets Toronto Green Standards Tier 3. To further reduce city water demand, rainwater is recycled from rooftops, impermeable pavements, and wastewater is treated with a living machine. In doing so, meets all water demand except for potable water, which for Ontario is restricted to municipal sources anyway. Also, to further reduce stormwater runoff, bioswales on site will filter water and return it back to natural aquifers below.
The existing HVAC system mainly consists of natural gas boilers sending hot water to original cast iron radiators in each room. The natural ventilation in the building relies on opening windows, which can raise heating loads in the winter. The new HVAC system will remove heat sources that rely on greenhouse gases and addresses occupant-reported discomfort, namely in the summer months. Our hybrid ventilation strategy features a dedicated outdoor air system, which is sized for the total required outdoor air rate. Additionally, natural ventilation is available in all rooms via operable windows. The atrium is only naturally ventilated, utilizing stack effect via operable windows and operable skylights. The building's cooling first utilizes multiple passive strategies to bring cooling loads down. This includes a cooling coil in the dedicated outdoor air system, window shadings, the shading of the roof PV system, and operable windows. Then, fan coil units are installed in select spaces needing additional cooling: the principal's office, the library, the multipurpose space, and the upper floor classrooms. The school is heated by radiant flooring throughout, and both the heating and cooling systems either reject heat to or extract heat from the ground. Geothermal energy generation is entirely renewable and a good fit for schools because of the large land requirement. The system's vertical boreholes will fit under the school's sports field. After the ground energy exchange, a ground source heat pump sends hot water through the radiant flooring or fan coil units to the spaces. The main consideration for this system is that the annual cooling demand is much lower than the heating demand. Addressing the source-sink imbalance can ensure longevity and efficiency of the system. To achieve this, the system is sized for the heating requirement, and additional renewable energy can be generated and rejected to the ground. Solar thermal panels will be installed on the roof to reject heat to the ground sink in the summer. This heat can be used for hand washing hot water in the winter months. As shown in this figure, the system is sized as double the heat makeup requirement, since the makeup requirement is only for the cooling season. Here we can see a plan of all on-site solar energy generation. Approximately 2,000 square feet of the roof is used for solar thermal panels. The remainder of the roof plus the parking shading structure make up over 30,000 square feet for solar photovoltaic panels. Finally, the extension facade features building integrated photovoltaic cladding for additional PV generation. The roof and parking panels will be at a fixed angle of 45 degrees, optimizing both summer and winter generation. The total on-site electricity generation is approximately double the school's estimated electricity usage, resulting in an excess of 270,000 kilowatt hours generated annually. This excess electricity is sent back to the grid, generating additional funds for the school or the school board.
Since the original building is 100 years old, professional analysis for toxin removal such as asbestos and mold must be conducted. The existing lead plumbing must also be replaced. Regarding the thermal comfort, the school's new HVAC system manages thermal comfort and indoor air quality. Also, multiple strategies have been incorporated to improve acoustic performance in the school. First is regarding the architectural design. Similar age group classrooms have been arranged near each other to reduce the noise distractions. Acoustic paneling will be installed in classrooms and an acoustic grid on the multipurpose area ceiling to reduce the noise of social activities which may disturb the library above.
Daylight analysis using climate studio simulation showed appropriate levels of illuminance in spaces such as the atrium, multipurpose area, and library. Classrooms also receive enough working light, especially near windows, and so these areas use daylight harvesting with daylight sensors to turn off lights when natural lux levels are adequate. To balance this with high heat gains, however, harvesting is mostly considered for east side classrooms, since the west side is vertically shaded to prevent rooms from overheating in the afternoon.
For the lighting fixtures, LEDs will be installed as they consume less energy compared to fluorescent lighting. Different fixtures will be installed in classrooms, atrium, corridors, group spaces, depending on lumen requirements. Also, pole lights will be installed on the school grounds to provide safety in low visibility conditions. In terms of plug load reduction, Canadian Energy Star certified devices are recommended, which can reduce energy consumption by between 20 to 65 of typical appliances. Beyond efficient fixtures, plug and lighting loads can be further reduced with motion sensing controls and auto scheduling. Further reduction relies on occupant responsibility, for example, to ensure appliances and equipment are turned off when not in use. This can be a learning opportunity for students to better understand and practice energy reduction strategies.
As a result of the aforementioned reduction strategies throughout our design, the energy use intensity for the site is estimated to be 23 kilobtus per square foot per year. This meets the Toronto Green Standard Tier 3 target, as mentioned earlier, and exceeds the competition requirement. Taking a look at the electricity end use breakdown for the school, we can see that the interior equipment or plug-in appliance loads takes up 40% of the usage. As mentioned, this could be reduced further through sustainable occupant usage.
This project considered the extent of its environmental impact in an effort to minimize embodied and operational carbon emissions. The design consideration and material selection considered the balance between emissions, performance, cost, availability, and material circularity. Some strategies employed in minimizing embodied carbon include the reuse of the existing building, a retrofit with minimal demolition compared to a new build, and minimizing the use of steel and concrete in favor of timber structures and finishes. Operational carbon emission is minimized with the renewable energy generation systems. Considering that this is a retrofit project with a new extension, the largest percentage of the greenhouse gas emission is attributed to the materials used to construct the vertical and horizontal components, accounting for a total of 74% of the project's carbon emission. Carbon sequestration provided by materials used in this project provides 58 pounds per square foot of carbon storage. Designing for durability and resilience is an increasingly important consideration with changing weather patterns and the risk of natural events due to climate change. This retrofit design considered prevailing weather patterns in Toronto, whose climate is characterized by large seasonal temperature and humidity differences. Future weather projections indicate increasing temperatures, fewer snow events, more summer storm precipitations, and more frequent heat waves. The effect of these projected changes, such as overheating risk, high wind-driven rain, snow loads, freeze-thaw deterioration of the brick masonry, are considered in the envelope design.
To provide water resiliency, the school will be storing 3,100 gallons of water in a tank located in the basement. In accordance with the Ontario Building Code, the fire-rated walls of the new school envelope prevents the spread of fire within the school, and 3 emergency exits in the building provides access to 2 muster points in the school site.
We estimate construction costs will be approximately $4.2 million at about $102 per square foot. This energy-efficient, high-performing retrofit school building and new extension can be constructed for about 25 to 43% less than a new build school of similar type and size in Canada. The upfront capital investment in the PV and BIPV systems account for 33% of the budget. However, it provides a cashback opportunity of approximately $19,000 per year for sending electricity back to the grid. The project also stands to benefit from the City of Toronto's environmental grant and incentives, such as the Energy Retrofit Low Interest Loan of 100% of capital cost with repayment terms of up to 20 years, as well as the Capacity Buyback Program, providing a one-time saving rebate of about $2,500.
As a net positive energy design, the retrofit eliminates future energy-related utility costs. Water utility costs are also minimized. This leads to 95% savings from the typical budget for these items, which would have been $46,000 per year. This plus cashback over 25 years totals to about $1.6 million, which may be put towards other retrofit projects. Beyond saving costs, this project aligns with goals in expanding school capacity and an energy efficiency set by the school board and by the City of Toronto. For stakeholders in the construction industry, the project considers ease of construction, sourcing local and available materials, and low costs. And to keep the school open, a phased construction timeline over 14 months is planned with temporary classrooms to accommodate areas under construction. Last but not least, design was done around the desire to provide students and the community with comfortable and enjoyable spaces to learn.
This retrofit project was approached with the understanding that buildings are made for people and that consideration should be made to optimize their experience within and around the space. From ensuring equitable access for all users to ensuring safety through various safety measures implemented throughout the site, the design provides a safe and inclusive environment for the occupants. The retrofit of the school also employs various biophilic design strategies to provide the occupants with a connection to nature in the built environment through sight and sound. Throughout the school, occupants' connection to natural systems is provided with a variety of systems around the perimeter. The project also highlights the rich history, traditions, and heritage and achievements of the school in the retrofit design. Considering that children are the future stewards of the environment, the project sought to create learning opportunities that will allow them gain knowledge on sustainability practices and strategies employed in this design. From the vented skylight for natural ventilation to the PV and BIPV systems for renewable energy. Proposed learning stations will provide information and live demonstration of these systems. The inclusion of a vegetable garden on site creates a farm-to-table experience and promotes conversation around sustainable crop cultivation and eating habits. This connection can be further extended to the community by partnering with Evergreen Brickworks, a community hub that promotes sustainability practices for future cities located a walking distance from the school. We consider this project to be of importance as it is reminiscent of the challenges that many elementary schools are facing. This presents an opportunity for this project to show how effectively we can upgrade schools with a design that is energy efficient, high performing, cost effective, and powered by renewable energy. It is our hope that this will serve as an example and a prototype for renewing city schools for future generations. Team Regeneration would like to thank our faculty advisors, Professor Mark Gogolevsky and Hayes Zenholt, for their support on this project, and our special thanks to the Solar Decathlon organizers for providing the opportunity for us to engage in this important competition. Thank you for your time and attention.